Okay. Sorry, that was a weird first thing to hear on the video. But I guess that's different than what I usually say. Usually on these videos they start with, okay, and then I say something else. Then I hack and cough a lot. And we go from there. Alright, so Le Chatelier's principle is the next thing we need to talk about. I think this is the first part in your notes, isn't it? Okay. This is kind of a fun concept. We might do something fun with this in class. We'll see how much time we have today. We kind of have a lot of residual AP questions to do from yesterday. But the idea of Le Chatelier is, and I'm going to say this a couple of times as we go through this, because this is a place where students were getting stuck last year. There's a difference between Q and Le Chatelier, okay? So I want to be very clear about this. You guys remember what Q is from yesterday when we talked about that? What is Q exactly? Okay, so what is called is the reaction quotient. And Q is before equilibrium is reached. Okay, so the time when you would use Q is when you've just put in the reactants, okay, and they haven't had a time to really get to equilibrium yet, and you're trying to figure out which direction is the reaction going to go to reach equilibrium. Okay, so that's Q. Le Chatelier Le Chatelier is a situation where we're already at equilibrium. And then we do something to disturb the equilibrium. Okay, and there are several things we can do to mess with it. All right, but from the very beginning, I want you to understand the difference between these two. All right, this is Q is when we are just putting things in, okay, and then they're getting to equilibrium. Le Chatelier, we're already at equilibrium, and then we do something like change the temperature, or change the pressure, or change the amount of one of the reactants or products that we put in. We add more of a reactant or product, and that's gonna disturb the equilibrium. It's going to push it one direction or another, okay? And so that's the difference between the Q and Le Chatelier, and that was sort of a source of confusion last year, so I wanted to just make sure that we understood that. And again, I'll talk about that at least a couple more times today as we go through this, I think, as long as I remember. Alright, so we're prepared this morning, that's good. If a stress is applied to a system at equilibrium, and a stress just means if we change something in the system, okay, if we do something to it, the equilibrium is going to shift to sort of reduce that stress, okay? So the three types of stress that we're really going to focus on here: changing the concentration, changing the pressure, changing the temperature, okay? Those three things, well, you know, you guys all have things that stress you out, right? This class is one of them, you know, the kinetics lab. Any other extracurricular activities you have, you know, job, that sort of thing. We all have stresses, right? The stresses for a chemical reaction, the things that stress it out: concentration, pressure, and temperature. Okay, if you change any of those things, the reaction is like, whoa, what's going on? Okay, it gets stressed out, and it changes a little bit. Oh, that was interesting. There we go. Okay, this isn't really put in the right place, but, you know, I didn't know where else to put it. We need to talk a little bit about the Haber process just because they mention it so much. So I want you to sort of be aware of this, okay? So the Haber process, that just says equilibrium at the top there. It's the equilibrium reaction of H2N2 and NH3, and you're just I would be very surprised if you did not see this reaction at some point on the AP exam. They love this reaction. They're gonna put it in there somewhere. Okay, it almost always shows up. So the Haber process basically is a way of shifting an equilibrium. Okay, because what we want to do here is we want to design a device that will help us to make as much NH3 as possible. Now, I don't know if you remember this from the other day, but even at fairly high temperatures, our equilibrium constant for this reaction is fairly low. Okay, and so the reaction N2 plus 3H2 yields 2 NH3. I think that's balanced. So there's your reaction, right? If the equilibrium constant for that reaction is low, even when you really raise the temperature, that means that we're not going to make much of the NH3, okay? Most of the concentration is going to be in the reactants. And that's a problem if we want to make a bunch of NH3. So this guy named Haber came up with an idea for how to do this, okay? And what he does, or what he did, was he designed this device that essentially pulls out the NH3 as it's being produced. Okay, which forces the equilibrium, and we'll talk more about this, but because he's pulling out the NH3 as you go along, then it means that the N2 and the H2 make more of the NH3, and then you pull that out and it makes more of the NH3, you pull that out. Now, if you let the NH3 just sit there, then this thing reaches equilibrium, and there's not very much NH3 that gets produced. But if you keep pulling out the NH3, that disturbs the equilibrium, and then the N2 and the H2 make more of the NH3. Okay, and that's how you can get a better yield of ammonia as you're going through this process. Okay, so you can see here, so you've got your gases here, and they go through a heating coil, and they go through a catalyst to make the reaction happen faster. And I mean, you just sort of follow the arrows up here. Okay. And as it goes down through here, you get a heat exchanger, so it essentially you're changing these into gases and then condensing them, and then you end up with this liquid NH3, okay? And then the NH3 is then pumped out, and then you recycle the N2 and the H2 that didn't react, and it goes back through the reaction again, okay? But you're essentially just pulling out the NH3 each time you go through the process and recycling the unreacted N2 and H2. Okay, so it's a very important reaction in industry, and they like this reaction. Okay, so let's think about an equilibrium mixture of N2, H2, and NH3 here for a second. So we want to know which way would the equilibrium shift if we added H2 to this reaction. Okay. So we don't really have any values for Q and K here, but we can kind of think about this a little bit if we write the equilibrium expression for this reaction. And the equilibrium expression here is going to be K equals, this is not balanced, by the way. Sorry about that. It may not be balanced on your paper either. You might have to write that in. It's not? Okay. Yeah, so go ahead and write that in. There's a 3 in front of the H2 and a 2 in front of the H3 in H3. Okay, so there's our equilibrium expression, all right? And so, let's see, I'm trying to decide if this is the best way to explain this. If we add H2, first scenario here, if we add H2 to this mixture, okay, then we're disturbing the equilibrium, okay? And so the equilibrium, we're applying a stress to the system, and the equilibrium is going to shift to help reduce that stress, okay? So maybe the best way to explain this is just to kind of think about the idea of stress. If we add a bunch of a reactant to this thing, what do you think the reaction is going to do in order to sort of fix that, help the stress to be reduced a little bit? Which direction might the equilibrium shift? Maybe towards the right, okay? We've got a bunch of H2 in here, and that's kind of stressful, so let's make more of the product, okay? So we add some H2 and that shifts the equilibrium to the right. I think that's probably the best way to think about it, maybe the most simple way, rather than thinking about Q and K at this particular moment. So we're going to shift the equilibrium to the right. Sorry, we're getting an announcement here. Okay, so the equilibrium is going to shift to the right if we add H2. To the right, meaning towards products. Okay. So we add a bunch of H2 into this thing. Eventually, we're going to end up producing more of the NH3. Okay, it's going to lead to an increase in the concentration of the NH3. What if we remove N2? So let's say that we pull out, we just take out some of the nitrogen there. Okay, so the nitrogen is now leaving. Which way do you think the equilibrium might shift then? Okay, so now the reaction is stressed a little bit because now there's not very much N2 left. And so some of this NH3 might start to break back apart to produce a little more N2 to sort of re-equilibrate. Is that a word? Equilibrate? I don't know. Sounds like a word. So the equilibrium is going to shift to the left, okay? If we remove the N2. To the left, or again, towards reactants. Okay, and then if we remove NH3, same sort of idea here, okay? And we already talked about this, that's what the Haber process is. You remove the NH3, and which way does that push the equilibrium? If we take some of this out, okay, again, that stresses the reaction. If we take some of the NH3 out, that's going to stress the reaction. So then the N2 and the H2 are going to combine to form more NH3 to reestablish equilibrium there. Okay, so we're going to produce more of the product, so the equilibrium shifts to the right. Again, toward product. Is it toward or towards that's not a word? Or am I thinking of something else? Are they both a word? Yeah, I never know which one to use, toward or towards. Anyway, it's not English class, so. Okay, so now if we want to think about it in terms of Q and K, if we add product, that's going to make Q greater than K, all right? So let me go back to my, did I erase my equilibrium expression? I did. Here, let's go ahead and write it again. Oh, that was neat. Let me try and write it again here. So K is going to equal, just so we have a visual here on what our equilibrium expression is, NH3 squared over the H2. I think I have this backwards from the way that it was written. Okay, so there's our equilibrium expression. So if we add product, now we're not at equilibrium anymore at that moment that we add the product. Okay, so now we're thinking again a little bit about Q. Q is when we're not at equilibrium. Okay, I keep saying K. Q is when we're not at equilibrium. Okay, I'm not saying K. Anyway, if we add NH3, then you look at our expression up here. That makes this Q larger than our K was. All right, so to reestablish equilibrium, the equilibrium has to shift back to the left. Okay, and then we get back to our K. If we remove reactants, that makes the Q less than K. So if we, I'm sorry, Q greater than K. Again, that's another way we can make Q greater than K. If we make the denominator smaller, okay, then that's going to make our Q bigger. And so then, again, it still has to go to the left. If we add reactant, that makes Q less than K. So if we make the denominator bigger, that's going to make our Q smaller than our K. And that shifts the equilibrium to the right. And then removing product makes the Q less than K. All right? Does that make sense? Thinking about how it changes the equilibrium expression? So then you just got to think about this. The reaction is sort of fighting to get back to equilibrium, okay? It's trying to fight to get back to this value right here. And that K is not going to change for a particular reaction as long as we're at the same temperature. We need to have the same equilibrium constant. So if we change the concentration of one of these things, then the equilibrium has to shift in order to get back to our K value. Okay? So again, I think this is maybe a little more confusing way to think about it, but mathematically, if it works in your brain to think mathematically like this, then that's just another way of thinking about it. Okay. If you determine the effect on Q, that will tell you the direction of the shift. Okay, so that's one way to do it. The other way, I mean, honestly, is just sort of any problems they throw at you on the AP exam, you can kind of think about what's going to happen to the equilibrium, and usually you can give a good enough explanation just by explaining that if we remove a reactant, that's going to shift the equilibrium back towards the reactants. If we add a reactant, it's going to push the equilibrium towards the products. Okay. All right. Changing pressure. So there are certain times when changing the pressure of a reaction would actually change equilibrium. Okay. The main time when this is going to be an issue, and again, this is unbalanced. The main time this is going to be an issue is if we have a gas reaction. Okay, obviously changing the pressure of an aqueous reaction really isn't going to affect things that much, okay, because you have solids and liquids there. Solids and liquids don't get affected that much by pressure, but gases do. Okay, so we've actually got some numbers on this one. Okay, it says at 472 degrees Celsius, the equilibrium mixture contains 7.38 atmospheres of H2, 2.46 atmospheres of N2, and 0.166 atmospheres of NH3. And it gives us the equilibrium constant. And it's asking, which actually this is going to help us with one of our AP questions today. What direction would the equilibrium shift if we cut the volume of the container in half? Okay, that's kind of an interesting question. So let's think about what happens if we cut the volume of the container in half. What are we essentially doing to those gases? So I have a big container, and then I change that to a small container. What's that going to do to the pressure of the gas inside the system? It's going to increase it, right? Remember we talked about the fact that pressure and volume, we talked about this in the gas unit, pressure and volume are inversely related, right? So if the volume goes up, then the pressure goes down. If the volume goes down, pressure goes up. Okay? So we are increasing the pressure in this system, right? Does that make sense? So if that's the case, again, we're applying a stress to this system, okay? And the system is going to shift to help reduce the stress as much as possible, all right? And so what's basically going to happen here, we have what you want to do in these types of pressure change problems is you want to count up the number of moles of gas that you have on each side, okay? So over here we have 4 moles of gas, and over here we have 2 moles of gas, okay? So notice, if we have more of the product, that's going to help reduce our pressure a little bit. Does that make sense? Because over here, we've got, I mean, if you want to think about it in terms of actual molecules, we've got 4 gas molecules on this side and only 2 gas molecules on this side. 4 gas molecules hitting the sides of your container, that's more pressure than just two gas molecules hitting the sides of your container. Does that make sense? Okay. So what happens is, if we increase the pressure of this thing by compressing it, the equilibrium is going to shift this way, because that's going to help reduce the pressure just a little bit of the system, okay? So the equilibrium shifts so that the pressure can be reduced a little bit, because we only have 2 moles of gas on the right side. Now, this is entirely dependent on the particular reaction that you're performing, right? Let's say hypothetically, now this isn't true for this reaction, but let's say we had a different reaction where we have 2 moles of gas on this side, and 4 moles of gas on the product side, okay? Then you increase the pressure and you actually push the equilibrium back towards the reactants. Okay, so the way you're going to figure this out is just by totaling up the number of moles of product and reactant that you have. Okay, and this only works, like I said, for gas type equations. Okay. So, a couple ways we can change pressure. First of all, by changing volume, okay? And that's what we just talked about, all right? This is a very typical one, and it's kind of a sneaky way to ask the pressure question, because they don't have to mention anything about pressure to ask this question, right? Like, I mean, just looking back at this question that was just asked, what direction would the equilibrium shift if we cut the volume in half, right? They're not saying anything about pressure. We have to understand what's going to happen to the pressure as a result of the volume being cut in half. Okay? Alright, so the system's going to move in the direction that has the least moles of gas. And then because the partial pressures change, then a new equilibrium is going to have to be reached there. Okay? So it's, again, this is another way we can apply a stress to our system. And it's got to sort of reestablish equilibrium at that point. It's got to get back to where it was. And again, this is basically just saying what I just explained to you. The system tries to minimize the moles of gas if the volume is reduced. And so it's going to shift to the side with the least moles of gas. And vice versa. Vice versa? I don't think that's right. Vice versa. Making a lot of grammatical mistakes this morning. Vice versa, that's like, I don't know what that is. There's a credit card joke in there somewhere. I don't know what it is. Okay, another way that you can change the pressure is by adding an inert gas. That's going to change the overall pressure of the system. Okay. What effect do you think that has on the equilibrium? Now, but first of all, we need to talk about what's an inert gas. What do I mean when I say inert? I'll give you examples of some inert gases. Helium, neon, argon, krypton. Okay, gases that don't react, right? Inert gases. So, if we say we're adding an inert gas, we're adding a gas that's not going to participate in the chemical reaction at all. It's just an extra gas in our system. It's going to increase our total pressure. What do you think that does to our equilibrium? So let's think about our equilibrium expression again for the Haber process here. We got NH3 squared H2 cubed into. Okay, so there's our expression. Let's say into this particular reaction we just pump some argon gas or some neon gas. Okay, does that change? You know what, I should have done this in terms of pressure instead of concentration. Hang on just a second. Just for the sake of my example here. Pressure of NH3 squared over the pressure of the H2 cubed times the pressure of the N2. Okay. Does that change the partial pressures of any of my gases that are up here if I add neon gas to the mix? No, it changes the total pressure, but it doesn't change any of these partial pressures. Okay, these partial pressures are all going to be the same. So I didn't change anything about my equilibrium expression when I added that inert gas, right? Only thing I changed was the overall pressure of the system. But adding an inert gas actually does nothing to the equilibrium, okay? Because it doesn't change our equilibrium expression at all. It doesn't change these partial pressures. Now, you reduce the volume, that changes these partial pressures. Do you guys see the difference between that? Okay? So, there's one way to change the pressure that does nothing to equilibrium. There's another way to change the pressure that does affect the equilibrium. Alright. So there's no effect on the equilibrium position if we add an inert gas. And they ask that question every once in a while in the AP exam. You know, what would happen to this equilibrium if we added 2 moles of helium or, you know, neon? And you'll have to recognize, okay, that's not participating in the chemical reaction, so it doesn't do anything to the equilibrium. Okay? All right, this is the big one, changing temperature, okay? I'm going to say this several times as well, and you need to hear this, and this actually makes sense based on what we talked about in the last chapter. The only thing that changes the K, the equilibrium constant, is temperature, okay? Now that's consistent with what we talked about in the last chapter. The temperature changed the rate constant as well, right? Okay, so the thing that changes your K is temperature, okay? So everything else you do as far as the Châtelier, it's going to mess with your partial pressures or your concentrations, okay, in your equilibrium expression. The only thing that messes with the K itself, the actual equilibrium constant changes it, is if you change the temperature, okay? So let me go back here for a second to show you something. Here we go, okay. This K right here, for the Haber process, 2.79 times 10 to the negative fifth, that is only the K at 472 degrees Celsius, okay? If I change that temperature, this number changes. All right, so you have to recognize that. That's what happens when we change the temperature. Get me through all this. So that's how we change the equilibrium when we change the temperature. I feel like I'm repeating myself a lot here, but I want you to understand this. Now, there's a really easy way to figure this out, and you can really think of this when you're trying to figure out which direction it shifts the equilibrium. You need to think of heat as either a reactant or a product, and that makes this much, much easier, okay? So, example here, if they ask you this kind of question, then what you need to know is whether this reaction is exothermic or endothermic, okay, because that makes a difference. So, this particular process right here, is it exothermic or endothermic? Okay, we have one piece of information that helps us with that. What is it? Delta H is greater than 0. Delta H is a positive number. If delta H is positive, that means it's an endothermic reaction, okay? So this is endothermic. Now, let's think about our definition of endothermic here for a second. When I have an endothermic reaction, what do I have to do in order to make that reaction occur? You have to put energy into it, right? You have to add heat into that particular reaction. So I could sort of, and I don't have a lot of room here, I'm just going to put it right here. I could think of heat in this particular reaction as one of the reactants. Does that make sense? The cobalt, oh man. Okay, let's think about complex ions here for a second, see if we can remember how to name this thing, okay? What is water? I can't remember. Is it hydro? Cobalt hexahydro? Yeah, I don't remember off the top of my head. That's horrible. But anyway, this is a complex ion. It's cobalt with 6 waters, okay? And then you got your chlorines right here, okay? And this thing is basically reacting. And on this side, when you have, and this is the one that I kind of wanted to show you in class. We'll see if I get it together enough to be able to show it to you, but it's kind of cool. You can shift this equilibrium by changing the temperature, and you can actually, just by changing the temperature of the reaction, you can get it to change from pink to blue, and then back from blue to pink. So you can put it in a hot water bath versus an ice water bath. You can go back and forth as much as you want, and it will keep changing from pink to blue, pink to blue, pink to blue, pink to blue, okay? You know, I always get asked that, and I always forget to look it up. I'm not sure if that's how mood rings work or not. It makes sense to me that could have something to do with the heat from your hand. You know, maybe the extra heat makes it change a certain color. I don't know. I'll have to look that up, because I always forget. That question was asked last year, and I just always forget to look it up. Yeah, there we go. Yeah. Okay. So we've answered the question. The process is endothermic. Which side do we put heat on? If we wrote it in the reaction, we'd put it on the reactant side. So then, if we're thinking of heat as a reactant, now you can sort of go back to the idea that we were talking about at the beginning. What happens to the equilibrium if we add a reactant? Because we're increasing the temperature, right? So increasing the temperature, we're essentially adding heat. So we're adding a reactant here. Which direction does that push the equilibrium? Towards products. Does that make sense? If you think of heat as either a reactant or a product, it makes these kinds of questions really easy. Okay? All right. It affects the rates of both the forward and reverse reactions, which, again, we talked about that in the last chapter. Okay? So it doesn't just change the equilibrium position, it changes the equilibrium constant itself. Because remember, well, you may or may not remember this, but the equilibrium constant is based on the rate constants. Okay? We talked about that in the very first section that we did in this unit. So then the direction of the shift depends on whether it's exo or endothermic. Okay, so you're changing the K, and you're also shifting the equilibrium one direction or another. So temperature is kind of the big one as far as if you want to make the most drastic change to the equilibrium, temperature can affect it a lot. Now, I say the most drastic change. I mean, pulling out the product as it forms, that's a very drastic change to the equilibrium as well, and that's the idea behind the Haber process. What happened? Nothing. Okay, so exothermic. I guess I got lazy and decided I'd rather write a D than a triangle. Sorry about that. Delta H is less than 0 for an exothermic reaction. Okay, that means it's going to release heat. We can think of heat as a product. Okay, which this is the opposite of what we were talking about a minute ago for endothermic. Raising the temperature, that's like adding a product if we raise the temperature, since heat is on the product side in an exothermic reaction. So if we raise the temperature, that's going to push the equilibrium back to the left towards the reactants. Shifts the equilibrium to the left. Okay, so then the question is, how does raising the temperature affect the equilibrium constant in an exothermic equilibrium reaction? If we're pushing the equilibrium back towards the left, that means that we're increasing the concentration of the reactants, right? Okay, so it's actually going to lower it. Again, if we think about, we've kind of been going back to our standard example here, just so you have a visual on this again. What we're doing here, if we raise the temperature, well, okay, this might be a bad example. I don't remember if this is exothermic or endothermic. Let's say this is exothermic for a second. Okay, because I honestly don't remember. But if it is exothermic, then when we raise the temperature of this thing, we're pushing the equilibrium back towards the reactants. That's going to make the denominator bigger, which reduces our K. All right? Endothermic is going to be the exact opposite. Let me just, oops, sorry, put all this stuff up here. And again, this is supposed to be a triangle. It's not that hard to figure out the triangle symbol on the notes. I don't know why I did that. Delta H is greater than 0. Produces heat. You could think of heat as produces heat. What? I just really messed these up. Sorry. Did it say produces heat on your notes also? Yeah, change that. It absorbs heat if it's endothermic. Okay, it requires heat. So you can think of heat as a reactant. Raising the temperature is going to push the equilibrium towards the products, which shifts the equilibrium to the right. Okay? Okay. The effect of catalysts. Now, they will ask this question every once in a while on the AP exam. I think we actually had this question on one of our AP questions. Actually, I think we had one on our last unit. I don't know if you remember that or not, but it was a catalyst question about how it would affect the ratio of something. The answer is, it doesn't change the equilibrium mixture, okay? It's going to cause the rate at which the reaction comes to equilibrium, it's going to cause that to happen faster, okay? So you can get to equilibrium more quickly if you have a catalyst, but it's not going to change the equilibrium concentrations or the equilibrium pressures of the reaction, okay? So it has no effect on the equilibrium other than it helps you to reach equilibrium faster. So if they ask you that question, they want you to make that statement, okay, that a catalyst has no effect on the equilibrium constant, and it really has no effect on the equilibrium concentrations. Okay? Alright, so let's do a little practice here. We've got an equilibrium in 204 going to 2 NO2, and we've got a delta H for that. So we're going to do some things to this and think about how that would shift the equilibrium. Okay, and really these are not that bad. Le Châtelier it's pretty easy once you get the hang of it. So if we add N2O4 into this system, which way is that going to push the equilibrium? It's going to push it to the right. Okay, and so that's going to end up increasing the concentration of the NO2 ultimately. So the question is, in what direction will the equilibrium shift? So we can say right here or towards products. What about if we remove NO2? If we take this out, what does that do? Having a lot of announcements this morning. Okay, so if this gets removed, then to reestablish equilibrium, the reaction needs to produce more of the NO2. Okay, does that make sense? So it's going to shift the equilibrium to the right. Is everyone okay with that? All right. If this gets removed, then the N2O4 is going to, some of this is going to end up making more of the NO2, and so that's going to reduce the concentration of the N2O4 ultimately. So again, it's going towards the right, towards the products. What about if we increase the total pressure by adding N2 gas? Wait a second, N2 gas? Where did that come from? Ah, that's an inert gas. That's not participating in this particular chemical reaction, okay? So what does that do to the equilibrium? You're trying to say it. Nothing, okay? It does nothing to the equilibrium if you add an inert gas. Remember, it increases the total pressure, okay, which they actually said that's what happens. But it does nothing to our partial pressures here, okay? So it doesn't change our equilibrium. What about increase the volume? This is where we compare the moles, okay? And now we have to, this is tricky because we have to think about this backwards from the way I said it before, because we're increasing the volume. What does that do to the pressure? It actually decreases the pressure, okay? So in order to reestablish equilibrium here, the system is going to want to shift to the side with the greatest number of moles. Does that make sense? Okay, because we're doing the opposite of what we were doing before. So the greatest number of moles of gas is over here, okay? So this equilibrium is going to shift to the right. So far we've done a bunch of stuff that shifts things to the right or towards the product side. Whoops, sorry, wrong one. Thank you. This one, if I was going to write anything for this one, I need to say, it does nothing. Okay, what if we decrease the temperature? A lot of random stuff happening this morning. So if we decrease the temperature, it might be helpful here to write heat as either a reactant or a product first. Our delta H is positive, so what kind of reaction is this? Endothermic, which means that heat is over here, okay? Heat is basically one of the products. We have to add heat to make this reaction occur. So if we remove heat, which is essentially what we're doing when we're decreasing the temperature, okay, the heat is leaving, then which way is that going to shift the equilibrium? To the left, because we're essentially removing a product, okay? So decreasing the temperature, it moves it to the left or towards reactants. First one that we've had that's like that. What if we add a catalyst? Okay, catalysts do nothing to the equilibrium. They just make the system reach equilibrium faster. Okay? I said nothing. It says which direction does it shift? Which direction? Nothing. That doesn't really make sense, but I mean, you know what I mean. It's not going to shift either direction, okay? If the standard heat of formation of NH3 is negative 46.19 kilojoules per mole, find the delta H for the reaction. Okay, I just thought I'd throw a little thermodynamics back in there just for fun, because we don't want to forget anything here, okay? We're going to do this fast, and this doesn't take very long, okay? I'm giving you the standard heat of formation of the NH3. It's negative 46.19 kilojoules per mole, okay? How does this equation differ from the standard heat of formation? Again, this is taking you back a ways here. Yeah, thermodynamics was tough. Okay, standard heat of formation is how much heat is either released or absorbed when you form 1 mole of the product. You guys remember that? Standard heat of formation is for 1 mole of the product. How many moles of the product are we forming here? 2. Okay, so we double our delta H here. Okay, so not that difficult to figure out our delta H. So we got negative 46.19 times 2. That's going to give me negative, my delta H here is negative 92.38. So actually I got lucky with my example before. It actually is exothermic. So negative 92.38, I should put kilojoules here. That's our heat change. Then determine how the equilibrium constant for this reaction should change with temperature. Okay. So, well, careful. This is a negative delta H, right? Which means it is exothermic. Okay. So heat is one of our products here. Now this is just saying how it should change with temperature, so we can kind of pick whether we want to talk about increasing or decreasing. I would say increasing is probably a little bit easier. If we increase the heat, we are essentially adding a product which pushes the equilibrium to the left. Okay, so what's that going to do to the equilibrium constant? And again, it might be useful to just write this one more time here. Let's see, we've got NH3 squared over the N2 times the H2 cubed. Okay, so if we're pushing the equilibrium towards the left, that means we are increasing the concentration or increasing the number in the denominator, which is going to do what to the K? It's going to lower it, okay? So increasing temperature, probably could have just written an up arrow there. Increasing the temperature equals the decrease in K. So essentially, for an exothermic reaction, it's an inverse relationship, right? And then the opposite would also be true. If you decrease the temperature, that's going to lead to an increase in K. All right. Okay, so Le Châtelier I think is pretty straightforward, pretty simple. Those are the main things you need to know about that for the AP exam. And we are done with the notes for this unit. All right, see you in class.